Alright, just a quick review. We have three subatomic particles that we want to talk about: the proton, neutron, electron. Protons, neutrons located in the nucleus of the atom. They account for the mass of the atom. Protons are positively charged, neutrons are neutral. The electrons, very, very small. Matter of fact, we don't even consider their mass when looking at different atomic masses. The electrons are located in the electron cloud, and they have a negative charge equal to that of a proton. Their mass is much, much smaller. Now, we know that all of these subatomic particles make up the elements. So let's look at how we symbolize these elements. We typically use either their symbol, or sometimes we will expand upon that just a little bit and use what's called their nuclear symbol. Their nuclear symbol tells us a little bit about the nucleus, tells us about the number of protons and neutrons in their nucleus. All elements on the periodic table are symbolized by one or two letters, with the first letter always being capitalized. You know, we have a few down at the end that have yet to receive a proper name from the International Union of Pure and Applied Chemistry, so until they receive that name, the Greek letters that compose, the Greek letters that are used to symbolize their atomic number will be used to refer to those elements. Now, so we use the symbol. I have carbon up here. Carbon, we know, has an atomic number of 6. We can look on the periodic table and get that atomic number on there. We know that the atomic number stands for the number of protons, and we typically symbolize the atomic number by the letter capital Z. The other part of the nuclear symbol in the superscript on the left-hand side is the atomic mass, or the mass number, rather, of that element. And the mass number is the number of protons plus the number of neutrons in that element. Well, let's talk about some varying types of atoms. Isotopes. Isotopes are atoms of the same element, but they have different masses. Okay? How do they get these different masses? Because we can't change the number of protons. We said that the nucleus accounts for all the mass. Well, they must have different numbers of neutrons. So I've got 4 symbols listed on the PowerPoint. They're all carbon-6. You know, carbon stands for C, or C stands for carbon. The 6 tells us the atomic number. We know that carbon has 6 protons. If it were anything else down in that subscript, it would be a completely different element. Okay, the top number tells us the number of protons and the number of neutrons. So in order to determine the number of neutrons, we can simply subtract the number of protons. For example, carbon-12 has 6 protons, so we know that it must have 6 neutrons. Carbon-11 has 6 protons, so it must have 5 neutrons. Carbon-13 has 6 protons, so it must have 7 neutrons. And carbon-14, which is our radioactive isotope of carbon, we use it for carbon dating, has 6 protons, and so that means it must have 8 neutrons. Alright, now what are all these different isotopes? How can we use this? What are they used for? Well, they all have different abundances in the world. And we use these different abundances to determine the atomic mass of these different elements. Okay? Well, how can we determine the atomic mass of these elements or these different molecules? Well, we use a mass spectrometer. And a mass spectrometer is an instrument that allows us for direct and accurate determination of atomic or molecular or molecular weights. Okay, so I have kind of a schematic, a simple schematic of how a mass spec works. Alright, you load the sample in here, and this in. The sample is then charged as soon as it enters the spec. Then the charged sample is accelerated using an applied voltage, so we're beaming, we're shooting a beam, if you will, of this sample. Alright, then the ions are passed into an evacuated tube. Okay. And there is a magnetic field that causes the ions to be deflected by different amounts depending on the mass. So the heavier, we're going to use kind of like centrifugal forces like in a centrifuge, the heavier elements are going to be slung, or are going to be separated from the lighter elements onto a detector screen. Okay. Once we get this detector screen information, we can then make a graph. And we graph signal intensity versus mass of the ion, and this is called the mass spectrum of that ion. We use all of this different information, okay, and we can get the various amounts of these different isotopes to calculate, we get these different masses from the mass spec, to calculate the average mass. Okay? In the real world, we use large amounts of atoms. Typically, you never see, or you're never going to see a chemist, well, we may in our time, but in the past and in present time, you're never going to see a chemist with a pair of forceps working with individual elements. So we work with large amounts of these atoms and molecules, so we must use their average atomic mass in calculations. Okay? We simply can't account for the individual masses of the individual elements. The average mass is calculated from the isotopes of an element weighted by their relative abundances. This is called a weighted average. We take their percent abundance, multiply it times the mass of that isotope, then add it to the different percent abundances, the products of the different percentage abundances of the different isotopes times their masses, then divide by the total number of isotopes, and then that's going to be the number for the average atomic mass we put on our periodic table that we use today. Just a little bit of a background as to how that number was determined and placed on our periodic table. You should know that the periodic table is used to organize elements in a very systematic, meaningful way. Elements are arranged in order of increasing atomic numbers, so they are arranged by their number of protons. We've got one proton here, two, hydrogen, helium, lithium, beryllium, and etc. Now, as we arrange these elements by their different numbers of protons, we noticed a certain amount of, noticed a certain repeating pattern in terms of chemical properties. This is known as periodicity or periodicity, depending on how you want to pronounce it. And this is how we get our different group numbers. Okay? So, the rows, the horizontal rows on the periodic table, 1 through 7, are known as periods. The vertical columns on the periodic table are known as groups. Elements that are located within the same group typically have similar chemical properties. So, for example, all of the alkali metals have similar properties, and in Chemistry 1 you should have placed a couple of these in water, and you should have noticed what they, or how they reacted with that water. Different elements, or these different groups have different names. Alkaline metals group 1, alkaline earth group 2. We have our transition metals groups 3 through 12, and then some underneath the stair step. Don't forget our lanthanides and actinides. Also, group 16 is known as our halogens. Group 17 are our halogens, and group 18 are our noble gases. Okay, cover that. The nonmetals are to the upper right-hand side of the periodic table. They are our above the stair step, if you will, that broad line. And don't forget about hydrogen. Hydrogen is a gas, though sometimes it can act similar to a Group 1 metal. We have our metalloids. Okay, and our metalloids have properties of both nonmetals and metals. Boron, you need to commit these to memory. Boron, silicon, arsenic, tellurium, antimony, germanium, sometimes polonium and astatine are also considered. Quick backtrack a second on nonmetals. You should remember some of these properties of nonmetals. Nonmetals typically are brittle if they are solid. They are dull in appearance and do not conduct heat or electricity well. Like I said, metalloids have properties similar to that of both metals and nonmetals, and our metals on the periodic table are below the stair step on the left side. Don't forget about lanthanides and actinides. They typically are malleable, meaning they can be spread into thin sheets. Ductile, meaning they can be drawn into wire. Lustrous, meaning they are shiny, and they are good conductors of of heat and electricity. That's why we use them as pots and pans, and also as in our homes for wiring. So that's some of the periodic trends. We're going to cover more periodic trends in a later chapter.